Hey guys, I wanted to show you, first of all, just kind of talk about it conceptually and then show you how to do total energy calculations. So this graph is something that I would put into your notes. And what it's showing you is like if we were continually heating something, let's say we had a hot plate and we were taking the temperature in Celsius, maybe, and plotting it about every 30 seconds. We would see it have a shape like this. So um, you have to, let's say you start with a piece of ice, and you can look up here and see that it kind of shows you the structure of the ice and how, um, you know, rigidly formed and everything it is. So as you're warming the ice up, like from -40 up to 0, which this is the melting point, which is also the freezing point. In this part, the ice particles are just moving faster. So this is called, this is where kinetic energy is increasing. And whenever we're talking about kinetic energy, the temperature changes. So we can use MCAT. So in this portion, we would use the MCAT equation and we would end up with a certain amount of energy, positive in this case, and it'll be in joules. Then when we get to the melting point, then the ice is going to start to turn to liquid. All of this energy is going to be now not going into making the particles move faster. So kinetic energy doesn't change, but what happens is potential energy changes. So this is where you're going to use the heat of melting. This is where you're going to use your packet, page 3. Here you're going to use page 2 for those specific heat values. Here you're going to use page 3. And you're going to calculate that energy by taking and essentially taking the moles times whatever the heat of melting is, which is something you can look up on the gold packet. Once all of the ice is melted and now liquid, then we start to increase kinetic energy again. The temperature is changing. The liquid particles are moving faster and faster. So we can use the MCAT equation again. This is going to be, again, using page 2, the specific heat for this, if it were water, liquid water. And then when you do this, you will end up again with the unit of joule versus down here in this plateau, you're going to end up with kilojoules. And you at the end are going to need to convert it to joules because you're going to try to figure out the total energy to take the ice from 40 degrees up to 130. So once all the liquid is turned to gas, you get to the boiling point here. This would be the boiling point or also the condensation point if you were cooling it. And again, no temp change. It's all the energy is going into changing potential energy to breaking the H bonds in the liquid so that it can start being formed as a gas. So you'll have both gas and liquid present here. Also, this plateau, you'll have both solid and liquid present. Until all of the liquid is turned to gas, then the kinetic energy will start to increase again. So when you're in this portion, again, just like when you were in the plateau before, you're going to use page 3. You're going to take your moles of water that you started with, and then you're going to multiply that by the heat of vaporization. And again, unit here is going to be kilojoule. You will want to convert this to joule. And then lastly, we have this slanted portion. Again, this is kinetic energy. The temperature is changing, so kinetic energy. We're going to use MCAT. We'd use specific heat of water as a gas. Answer will be in joules. So kinetic energy, potential energy changes, kinetic energy, potential, and kinetic. So when you have a phase change like this, you're actually going to have, let me try to change colors, 1, 2, oh, 3, 4, 5 calculations, and then at the end you add them together. So now I just wanted to talk to you in general on how to do these calculations. These are the steps that my brain kind of thinks through when I'm doing these. If you don't already have a drawing of the graph, you would want to kind of sketch it out. And then you're realizing that, here would just be time as the reaction or the process progresses, and over here would be temperature in Celsius. And then let's say, you're heating something up. You're going to want to sketch something that looks like this. And then if you're cooling, it'll look the reverse. And again, it would be Celsius, temperature, and time. So then I would label, so here we have changes in kinetic, potential, kinetic, potential, and kinetic. Over here, kinetic, because temperature is changing, potential in the plateaus, and kinetic in the sloped parts of the graph. And then I would star the graph wherever the starting temperature is and the ending temperature. So let me show you what I mean. So here's the problem, and we are cooling water. So because we're cooling, when I draw this, I would slope it downward. And I'm going to get a little messy because I'm not the best at writing, but I'm going to just draw that general kind of sloped down shape. And then I'm going to also label the temperature at those spots. So this would be the melting point and the freezing point. This would be the boiling point and the condensation point. So in this question, for water, this value here would be 100, and this value here would be 0. So in the question, they're asking for the water to go from 25 degrees, which is going to be down here somewhere, and then it's going to go down to negative 25, so down here. So you're going to really have 1, 2, 3 calculations. So when you start the calculation, I'm going to start, and I can even number these. So my first calculation is going to be a kinetic energy calculation. So I'm going to be calculating based on that temperature change and using the specific heat of liquid water. So over here, page 2 of my packet. So I'm going to take and use MCAT. So Q is MCAT. So I'm going to put in my 120 grams. Specific heat is 4.18 joules over gram degrees Celsius. And my temperature change is 0 minus 25 degrees. So I am going to end up with a negative, and I'll end up with negative values for all of these because this is an exothermic process. So when I do this, I end up with negative 12,540 joules. I'm going to convert to kilojoules, so it'll be negative 12.5 joules. So it releases that much energy when I take water at 25 and bring it down to 0. So this is one of my energies that I'll add. Step 2, or this plateau portion, I'm going to be calculating potential energy. And when I do that, I take moles times my heat of. In this case, I am going to use the heat of melting. And that can be found on your gold packet, page 3, dealing with water. So the value is 6 kilojoules per mole. For the heat of melting, we are going to use it as a heat of freezing or fusion because we're in the cooling process. So we would want to take and use the negative value. So my moles, I would take 120 grams. My pen is going crazy. And I would want to convert that into moles. So 1 mole of water has a mass of 18,016 grams. And then times that negative 6 kilojoules in 1 mole. And you can see the grams, the moles cancel. I'm in negative kilojoules again. And I end up with negative 39.96. So you could say negative 40 kilojoules. All right, so we've done the calculation now for the amount of energy to take the 25-degree water and lower the temperature, so kinetic energy. It's going to be an exothermic process, negative value of a negative 12.5 kilojoules of energy are going to be released. This portion here, the plateau, we're going to calculate the potential energy change, taking the grams, converting to moles, so we have moles, and then multiplying by the heat of fusion or freezing. And that value is on our packet, and it's going to be negative because it's going to be an exothermic process. So those are the first two. Now we're going to do calculation 3. So we're in the sloped part again. So we're calculating kinetic energy. So we're going to use MCAT. And when we do this, again, we'll take our 120 grams times, now we're dealing with water, ice. So we're going to use this value, which is 2.09 joules per gram degrees Celsius. And then our delta T is final. We're going to end at 25, negative 25 minus initial. We're starting at 0 degrees. So when we do this, we end up with negative 6,270 joules. Converting that to kilojoule would be negative 6.27 kilojoules. So to calculate the total energy, I am going to add and make sure they're all in the same unit. And in this case, they're all in kilojoule. Add those 3 numbers together. That will be how much energy is released in this case. So my total energy is going to equal 12.8. Sorry, I can't read my own writing. 12.54 kilojoules plus, and these are all negative, so you'll get negative at the end, plus 40 kilojoules plus negative 6.27 kilojoules. So I end up with about negative 59 kilojoules. I hope that helps.